Yeah? What is the most non-trivial, most celebrated theorem about compactness? Say it? No, that is an application. That is not such an important theorem. Come on, anybody? The product of any collection of compactness is compact. That is the thing. Absolutely any collection. That is, who is the author of this theorem? No, same as the embedding lemma fellow. What is his name? No, it is known that way. Just as there is Urysohn metrization theorem, there is somebody's compactness theorem. What is it? Tikhonov compactness theorem. Tikhonov compactness theorem says that the product of any collection of compact spaces is compact. Right? So it's very easy to give examples of compact T3 spaces which are not metrizable. Metrizability is not preserved under arbitrary products. It is preserved under countable products. The product of countably many metric spaces is a metric space. That is why compactness is called a productive property. Okay? Productive doesn't mean that it produces more theorems or anything. Again, in fact, with Lindelof things are worse. Even the product of two Lindelof spaces may not be Lindelof. There are examples, counter examples. For example, the Sorgen-free line or semi-open interval topology. That is Lindelof, but when you take its product with itself, it is not Lindelof. Okay, so that is going to fail. The next one. Then you come under an entirely different way. Countable base means there is a countable collection which is a base, right? I think again something is missing or what?
There is more about
Okay, never mind. I'll do it separately. See, this is what I wanted. No, let us have the full one. The full one. I wish we had sit together and decided this. A locally finite base. What is so great about compactness? The word finite in the definition of a topological space. So, if you have a compact things, then you can sum. You can add, just as you can add a finite number of functions. Now, locally finite means we say that a base is locally finite, or any collection is locally finite, if there exists a neighborhood of this point which intersects only finitely many members of the collection. That means the collection can be infinite. But as far as my world is concerned, I can comfortably stay in a neighborhood which intersects finitely many. Like there are so many people in the world, but in my neighborhood, how many people will I be able to connect in a small neighborhood? Only a finite number of persons. Of course, you may say that the entire world is finite, that is a different matter. So, will this work? Well, unfortunately, that also fails. Locally, finite base works, but rarely applicable. Give me some metric spaces which have a locally finite base. Remember, locally finite means every point has a neighborhood which meets only finitely many members. The space may be big, I don't care. But as far as my surroundings are concerned, it is locally finite. Can you give an example of a locally finite base or a metric space having a locally finite base? Well, take the real line, the most familiar. Yeah. Does the real line have a countable base? Does it have a countable base? Is there a collection, countable number of open intervals, such that every open set is a union of them? Come on. For example, yes, you take rational and intervals with rational endpoints, PQ. Now give me any open set, suppose this is the open set AB. Well, I take such collections for every pair, P1, Q1, then P2, Q2, P3, Q3. Because the rational numbers are one blank, this is a base. What is that? Because of which property of rationals? Countable. Countable means as a result the collection that you get is countable. But why is it a base? Why is it sufficient to form a base? No, that is also countable, but that is not the crucial point. Huh? Denseness. No? Countable rationals are found all over. Like people from Kerala, now that I am in Kerala, you go to any part of the world, you will find some Keralite there. Try it. I mean, it's a compliment, of course, but same with rationals. You take any open set, you will find some rational there. So, how do you show that these sets form a basis? Well, you take any AB, then form all possible such collections. You will not miss any point. Because suppose this is a bad point which you miss. Well, near this point there will be some rational as close as you like. So you take that interval, very small interval, with rational endpoints, that will cover that point. So the collection of all open intervals with rational endpoints is a countable base for the usual topology. But is there a locally finite base? Suppose I give you a point. Take 0, for example. Does it have a neighborhood which means only finitely many members of this base? Again, because of denseness of rationals. In fact, that is going to happen in any metric space. You take X, now you take a ball. Now suppose by magic this ball intersected only finitely members of the topology. Then it will intersect, these will be some balls. Then. Now you take those, there are only finitely many centers. You take a real number which is less than the distances of all of them. Now what will happen? It is disjoint from this, it is disjoint from this, it is disjoint. So it doesn't meet any member. So unless there is one exception, if the topology is discrete, then it will work. Because With discrete, there is a trivial locally finite base. What is it? For every point, just take only that point. That is enough. That is a neighborhood. It is an open set. And the collection of all such forms a locally finite base. Because given any point, take that singleton point itself. That is an open set which meets only finitely many because it doesn't have anything else. So, locally finite works but rarely applicable. It works only in a very extreme case. So it's of no use. It fails even for real line. Then sigma locally finite works. So I think I'll have to probably stop because this is where the general metrization theorem begins. Now it is all given in the appendix. So I'll give definition of sigma locally finite. That sigma, by the way, have you seen it anywhere in mathematics? Sigma? Anywhere? Come on. No, in other areas of mathematics. Say. What? I didn't get you. Mesh. Measure, yes. Sigma algebra. There, sigma algebra means a collection which is closed under countably many. And then it's an F sigma set. Have you heard of an F sigma set? What is it? It is a collection of countable number of closed sets. Normally it will not be closed, but it is the next best thing to close. And what is the opposite of that? Sigma? Delta. Very correct. G delta set. So sigma really means I can drop this sigma and I can say countably many, countably locally finite. That is probably a better word. In fact, Mankras uses that definition, that word. Although conceptually it is the same. So instead of a locally finite base, if you take a countably locally finite base, now what does it mean? That means a collection B countable collection of families, each of which is locally finite. The entire family may not be locally finite. This may not be locally finite. But each of these BNs is locally finite, and it is the union of members of this. So that it turns out to be the right condition. And what is so nice about it? Let us take the next one. That is more a detail. No, I think somewhere. Okay? Improvement means weakening the hypothesis. Okay, but how much can you improve? How much can you improve if you are a good purchaser? If somebody buys a Maruti for 5 lakhs, you buy it for 4 lakhs and you claim that you are a better deal. Somebody can buy it for 3 lakhs. What is the ultimate? Free Maruti. Nobody can buy it for less than free. Because if that is the case, then that will be, okay, take this Maruti and also take this 1 lakh rupees. I don't think there is any seller who does that. So when you try weakening some hypothesis, ultimately a level comes where it is necessary, in fact, it is not only sufficient. What is weakening means? That means keeping sufficiency get weaken. But ultimately a level comes where it is necessary also. So when you get some condition which is necessary as well as sufficient, that's the end. That's the end. No further improvement can be made. It is tight from both the sides. So sigma locally finite does that. Okay, now, as my friend was saying, I need to take a short break. But I was under the impression that the time is already up. So, depends on your that program, isn't that going to be applicable?
That all of them have D and Govt.
Okay, then we can have a more informal one, because as far as this theorem is concerned, it is already covered in the book, and there is not much point in repeating what is already here. So, how long will we take?
15 minutes. Let us all have tea and come back. 15 minutes.
Within 15 minutes, can they finish the tea?
Tea is here, right?
Oh, it is right here. But do they know? I mean, those who prepare tea, will they know?
No, it's here. It has arrived.
Okay. If you think 15 minutes is enough, then okay. So, right now it is almost 12. So, let us meet, say, 20 minutes after 12. Then we'll continue up to 1 or earlier.
Since there is no other speaker, yeah, we are free to.
Okay.
Sit down.
Yeah. Oh.
So all the stuff in the original thing will be there somewhere at least. That's all. But maybe because I couldn't send you earlier. Yeah. Earlier. Yeah. So in the initial pages there was this summation business. Partition solidity. It is after that you wrote pseudometric.